Now for the next speaker, it will be Mr. Joachim Nordin from Siemens Energy. He's Decarbonization Strategy Manager. That's a nice title, Joachim.
Yeah,
Capability to use green fuels, including hydrogen in gas turbines. And I would like to say welcome back to Finspång. You were here at the Green Connections 3 years ago, and welcome back. And take it from here, Joachim.
Yeah, I think it was a colleague of mine that participated last time, but nevertheless, thank you for being here and be able to present. So, I will talk about a green future for industrial gas turbines and the challenges with fuel flexibility. And I represent the Swedish side of Siemens Energy. And since the start in 1913, the Siemens Energy turbine business in Finspång, Sweden has delivered more than 1,000 gas turbines, 2,300 steam turbines, 50 heat pumps, 50 power plants to 115 countries. So it's quite the legacy. And our current offerings are focused around medium-sized gas turbine with an electrical output of 24 to 62 megawatts in simple cycle operation. And we also have industrial-sized heat pumps in a range between 15 to 40 megawatts of thermal output. And when it comes to decarbonized fuels for gas turbines, we have many different options with regards to feedstock, such as biomass, e-fuels from renewable sources, or even fossils with carbon capture, utilization, and storage. The fuels can come in liquid phase or maybe gaseous phase, and their chemical compositions vary a lot with a huge variation in characteristics. This gives a very diverse landscape in the available options regarding decarbonized fuels. Siemens Energy works with multiple different fuels at the technology development level. And the more mature options are already released or are in the product development phase. The more prominent variants are hydrogen, that we currently offer at 70% volume, co-firing with natural gas. And we are targeting to have 100% hydrogen capabilities latest 2025 in our products. Cracked ammonia, that means that it's a pure stream of hydrogen and nitrogen when you have cracked ammonia into its components. That one we currently offer at 50 volume% co-firing with natural gas. If you look at the liquid side, we offer HVO100 biodiesel as an alternative. And there are many options on our roadmap for the future that we're looking into and investigating. So the path forward is kind of volatile with many disruptive elements. And we believe that through collaboration and partnership, we get a clearer view together with our customer of what the future holds. If we go into characteristics of the alternative fuels, they differ significantly compared to the traditional fuels used in gas turbines, such as natural gas or traditional diesel. The picture on the bottom left is from our atmospheric combustion test rig, where we have optical access to the combustion chamber and the burners. And we can clearly see here when we increase the amount of hydrogen in the burner from 0, that means pure natural gas, up to 100% hydrogen, that the shape of the flame becomes much thinner and it's situated much closer to the burner tip compared to the natural gas case. These changes in behavior needs to be adapted for in the design with special considerations. And our current capability of 75 volume% hydrogen in our combustion system, that corresponds to a CO2 reduction of around 50%. But as can be seen on the chart to the right, there is a non-linear behavior when you increase the amount of hydrogen. So each step on the development path going forward is steeper and more difficult to take compared to the one previously done. So the special characteristics of hydrogen becomes more and more dominant as we increase it. And we'll end up in a state that you can see in the picture to the left with a very changed behavior, how the combustion behaves in the gas turbine. An alternative way of storing hydrogen in its pure form is to use ammonia as a hydrogen carrier. This one can be especially attractive if you want to have long-term energy storage, or maybe if it's a long-distance shipping of large quantities of energy. We believe that fully cracked ammonia is the best option suitable for us, and it offers very good synergies with the development we are doing on hydrogen as a fuel. We have successfully already tested fully cracked ammonia at 100% fully cracked ammonia in high pressure single burner tests at the Clean Energy Center in Berlin. And that is done under real gas turbine conditions with full pressure, full temperature conditions and everything. And regarding biodiesel, there are many different alternatives with biodiesel, and there have each specific characteristics. HVO100 has been tested during a cooperation between Siemens Energy and Göteborg Energi at their site, RYA, Combined Heat and Power Plant, situated in Gothenburg. HVO100 has since been released as an approved gas turbine fuel to be used in our products from Finspång. And when you compare HVO100 to other types of biodiesels like FAME or ME version, there's a clear distinction in the characteristics. HVO100, it's much more closer to an ordinary diesel fuel. However, there are differences. The FAME or ME version, it behaves differently with regards to how it evaporates, mixes with the air, and how it combusts and burns in the combustion chamber. So the green fuel examples I've talked about give you a good flavor of many of the challenges when it comes to designing robust and flexible gas turbines, as each fuel that might be a potential candidate for the future has special characteristics and will dictate how you design the systems. Throughout the year, we have gained a lot of knowledge and experience about green fuels, and especially hydrogen. On this timeline, you can see some of the highlights when we first achieved different major milestones on our path into a sustainable world. 2016 marks the year when we invested in-house additive manufacturing capabilities that has greatly enhanced the development speed and opened up for more advanced design that can be tailored for the specific characteristics of different fuels. The effect of this enhanced development speed can clearly be seen on this timeline as the achievements are stacked up more tightly the last years here. And lately, this year, we have invested in a dedicated green fuels test engine that will unlock more testing opportunities for us and further accelerating the development pace with a target to reach 100% hydrogen latest 2025. So how do we achieve this? The traditional development cycle that we use is that we start off with advanced simulations, but they need to be calibrated based on previous experience and test data, especially since many of the green fuels behave differently compared to the knowledge base that we have on natural gas. You really need to gain more experience to put into and calibrate the simulation models. And when we're satisfied with the simulation results, we go over to the rapid prototyping using our additive manufacturing capabilities. So we reduce the lead time to when we can have the prototypes ready and test them out. And the additive manufacturing also enables better designs. Next step is testing. And here we have multiple different options. First off, we use single burner rig testing at atmospheric pressure conditions, but we can simulate the real temperature conditions in a gas turbine. And we can evaluate the results based on correlations from historical testing, how the testing corresponds to real gas turbine conditions and full engine operation. When we're satisfied, we take the best performing burners and we go to the Clean Energy Center in Berlin, where we can do single burner tests at real gas turbine operating conditions. From that, it's scale up for full engine testing. For the smaller gas turbines in Finspång, we have two test cells that we can use. They are used either for factory delivery testing before we ship our products to customers, or they are used for R&D green fuels testing, where we can use multiple different green fuels to evaluate and test. For our largest gas turbine from Finspång, the HVO100, we have built a separate test facility with a complete gas turbine string. So this is the green fuels test engine that I was talking about previously on the timeline. Due to the larger fuel consumption, we had to be clever how we configure this test engine, since availability of hydrogen currently is a bottleneck for us. And a couple of years ago, we actually used all the available trucks and trailers with hydrogen in Northern Europe during one of our test campaigns. So the logistical side and challenges there are quite immense. The system we developed is a 5-burner sector system. This system lets us run the gas turbine using all of its 30 burners, but we only feed 5 of the burners with hydrogen. Thus, we save a lot of hydrogen fuel and giving us maximized running time to collect more experience and data. The 5-burner sector is also equipped with special measurement equipment so that we can evaluate the results as if the complete engine would have been operated on hydrogen. To better understand the challenges with renewable energy, we have a microgrid built up at our test facility in Finspång that we call Zero Emission Hydrogen Turbine Center. There we have solar panels, electrolyzer for hydrogen production, it's a battery storage system, and hydrogen storage. And that hydrogen storage, we use that for our test campaigns in combination with externally sourced hydrogen. And we're putting in some investments on the hydrogen storage capacity, and we'll increase the storage capacity by a factor of 4 the next year. Besides the core combustion technology, there are also many other considerations to take into account in the design when it comes to green fuels. For hydrogen, there are many adaptations needed on the auxiliary system, like the fire detection, gas detection systems, and seemingly simple systems need to be adapted, such as the enclosure ventilation system. This is due to the different behavior of hydrogen. It will disperse differently in the enclosure in the event of a leakage. And the high reactivity will also make you do changes and adaptations, so you still have a safe system that satisfies all the safety regulations on the market. Already today, we offer our gas turbines as hydrogen ready. We have developed a concept that has been certified in Germany by the regulations TÜV Süd. That means that you can purchase a gas turbine today, knowing that it will be possible to upgrade it in the future when you have hydrogen available at your site, to avoiding the risk of stranded assets. Chalmers University in Gothenburg, they have modeled the competitiveness of hydrogen-fueled gas turbine for a zero-carbon Europe. And in one of their models, they have simulated a city with about 250,000 citizens. The main conclusions are that gas turbines have an important role to play in renewable energy systems, and that fuel flexibility further strengthens the competitiveness. And at Siemens Energy, we offer a broad range of different gas turbines to suit specific customer requirements. They are ranging from as low as 2 megawatts all the way up to 593 megawatts. And we believe in a green future for gas turbines, and that they will play a vital role in a renewable energy system for the future, with a lot of characteristics and features that are well suited for the needs of the future. Thank you very much for listening.